Hello and welcome to this MCMA webinar, a practical approach to building a real-time industrial Ethernet network for automation. My name is Joanna and I will be serving as your moderator today. Attendees that have joined this webinar have joined in listen-only mode, which means that you are muted. If you do have a question during this webinar, please submit them in your questions panel and we will answer all questions at the end of this webinar. As a reminder, this webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to introduce our presenters for today's webinar, Sari Germanos and Siddharth Ravikumar. Sari is the Technology Marketing Manager for Ethernet Powerlink Standardization Group. His expertise lies in developing complex, distributed, real-time mechatronic applications. He also has significant experience in applying simulation technologies to improve the efficiency of developing large-scale distributed systems. Sari received his master's in computer science from Boston College. Siddharth is a senior consultant at Calicito with a focus of solution building in real-time industrial networking in IoT space. Experience in development of networked industrial products with hands-on experience in all phases of product lifecycle. He is an electronics and communications engineer with a passion for robotics and automation. Calicito offers consulting and offshore services with a focus on real-time industrial networking and IoT for customers in European and U.S. markets. I'd also like to thank our exclusive sponsor of today's webinar, B&R Industrial Automation. B&R combines state-of-the-art technology with advanced engineering to provide customers in various industries with complete solutions for machine automation, motion control, HMI, and integrated safety technology. With real-time Ethernet standards like Powerlink and Open Safety, as well as the powerful Automation Studio software development environment, B&R is constantly redefining the future of automation engineering. And now I'd like to hand it over to Sari for today's presentation.
Thank you, Joanna. So the point of this webinar is to show how we can use an open source solution to create a real-time that is both high quality and high performance. And so we will start by talking a little bit about remote I/O in general, how that's used in machines, and then we'll talk a bit about Ethernet and why we use Ethernet. We will then jump into the requirements of a real-time network, and then we will talk about some use cases. After that, I will pass this on to Calicito, and they will talk about some of the solutions that are available today on the market, again in open source form. So the whole point here is that when we talk about a machine, we have a general architecture in mind, and the ideal architecture for a machine is that you have one real-time network in a machine that connects all the components together. So a PLC can control a robot arm, or can control a safety system, or can look at the vision systems, control pneumatics, I/Os, all sitting on one network. If we think about a typical machine today, this is a classic structure today. So typical machines on the market usually have several buses. So one bus could be doing some kind of motion control, another bus could be doing some I/O and some maybe controlling a couple of XCs. A third bus might be used for safety. In the ideal world, this would not be a good way to go, because you have many bus systems and you have different engineering tools trying to debug this machine, and so you have complex diagnostics and maintenance that you have to worry about. So if you were able to take a system like this and collapse it into one network, you'd end up with this type of a structure, and that's what we're shooting for. So you have one technology, and then you have freedom of machine design and freedom of layout, and then you have very easy diagnostics and maintenance because you're only using one set of tools to look at the whole machine. So Fieldbus technology is not new. It's been around for a long time. So things like RS-485 and CAN have been used for a long time to do remote I/O. But when it comes to trying to do motion, or when you have systems with a large number of nodes on the network, traditional Fieldbus is very limited in their bandwidth. So we started looking at Ethernet because Ethernet is freely available. It's available on most microprocessors today. And it's a standard that's been around since 1972. The problem with Ethernet is it's not deterministic. So even though it gives you the bandwidth that you need for automation, Ethernet in of itself cannot give you the determinism because it's based on collisions. And if you have packet collisions, then you have retransmits, and so you have indeterminate amounts of delay in a network depending on how busy the network is. So in order to mitigate that, people have tried to use switches. So there are some automation machines out there that use switched Ethernet. So things like Ethernet IP or Profinet are using switches. The problem with switches is that, first of all, they're expensive because in order to do automation and real-time control, you have to have a switch that is configured specifically for the application of that machine. So there's a lot of putzing around with the routing that you have to do. Secondly, switches have inherent delays in them. And then, depending on the number of queues that are available in your system, you might end up with queues, and if the queues are not long enough, you end up with packets being dropped and having to do retransmits. So they cause a lot of complexity, and they're quite expensive. So ideally, you'd like to be able to control or eliminate Ethernet collisions without the use of switches. And that is what we try to do with Ethernet Powerlink. So if you think about the ideal network requirements today, in order to have an efficient machine, you really have to have a network with real-time performance and high efficiency. You need to have a large asynchronous bandwidth because you might be passing around large amounts of data, not just for command and control, but you might be doing some video imaging, you might have some image recognition going on, so you need to be able to pass this kind of data on the network without experiencing significant delays or jitter. You'd like to have one network for all automation, which is what we discussed before. You'd like to have a flexible network topology and hot pluggable. You need high availability because machines cannot be down. It costs money for a machine to be down on the manufacturing floor. And you'd like to be immune to electromagnetic noise. And lastly, you want to be able to easily commission a machine and have easy ways of maintaining it and diagnosing it. And there's some requirements that are put on the network for that purpose. So if we think about the first two requirements, the way we're going to address this now in the context of a protocol called Ethernet Powerlink, which is an open source protocol. So the idea behind Powerlink is that you eliminate Ethernet collisions in the protocol itself to guarantee that no collisions ever happen, and therefore you never need a switch. So you can have an entire network that's based on hubs. So protocols like this require that you have a network master. So in this case, Powerlink has a network master called the managing node, MN, and then everything on the network is called a control node. So you have one managing node, and then all the slaves are control nodes. The idea here is that we have the concept of a cycle. So a cycle is defined to be the amount of time taken for every component on the network to share the data that it has to share for that cycle. So if you have a 200 microsecond cycle time, that means that you're sampling the IOs every 200 microseconds. You're looking at the value of the axes, what they're doing every 200 microseconds, and you're passing controls to the axes every 200 microseconds. So that's what a cycle time is. So here's your entire cycle. Now the cycle here is split into two components. During the first phase of the cycle, we do all the real-time communication. So the PLC might send a command to an axis, or it might read the value of an IO. During the second phase of the cycle, we reserve some time to do standard IP communication. So if we're trying to pass some image data from a camera and put that on our CPU, we can do that. So the way this works is that the cycle starts by the network master, which is in this case the PLC, putting out the start of cycle frame, and then it sends individual pull requests to each component on the network. When it receives its own pull request, it then publishes one packet of data. So that's the sequence now going on. Your start of cycle frame comes in, your first pull request comes in, and then the response goes out. The second pull request comes in, the second response goes out, and that keeps on going until you've addressed every component on the network, and then you start your asynchronous cycle, and then you put out your asynchronous data, and the asynchronous data, that's standard IP, is also scheduled. So even when you're doing TCP IP or UDP, there are no network collisions that take place because all those packets are scheduled. So as a result, you end up with something that's a very easy protocol to manage. The protocol is very, very simple. There's no complex time synchronization. So the startup cycle frame is there every cycle. So that's what synchronizes the whole system every cycle. And everything happens on one medium. Now, another nice effect of Powerlink is because we are using hubs, all the responses coming from the components on the network go out in broadcast mode. So if you look at things from the encoder's point of view, when the PLC puts out the startup cycle frame and then sends out the first pull request, and the encoder puts out its value, that value goes to everybody on the network at the same time. So if two components on the network need to share data, that data does not have to go through the master and then back to the node that it's intended for. The data is there every cycle for every component. So you can do node-to-node communication every cycle, which is very unique in industrial Ethernet. So the big deal about having one single network for all automation is that you might have a slow component, so something like a pressure sensor or temperature sensor where the values don't change that often, and then you might have a component, say like an encoder. You need to read an encoder much more often than you need to read a pressure sensor. And here Powerlink has something called the multiplex slot assignment. So in order to, the way that works is that if you take a look at the sequence of cycles here, the first cycle components 1, 2, and 3 communicate, then components 4, 5, and 6 communicate, and then your asynchronous frame. In the next cycle, 1, 2, 3 go again, but then 7, 8, and 9 multiplex those 3 slots. And then 1, 2, and 3 go again. Obviously, 1, 2, and 3 are the high frequency guys. And now 10 and 11 use 2 slots, and now there's an empty slot. So here we're able to multiplex 8 data frames between much fewer components. So you have three slots where you're sharing data from 8 components. So there's another form of efficiency called poll response chaining. So when you send out a poll request, instead of sending out a poll request for every component on the network, you can send out a general poll request, and then each component responds with a fixed time delay. So again, you don't end up losing time for the poll requests. So you just put out your data one after the next, and that's just a form of efficiency. So if we think about hot pluggability and high availability, well, hot pluggability is quite easy because in this case, each Powerlink component actually has, first of all, it's using standard Ethernet. Secondly, each component on the network has 2 Ethernet ports that are connected internally by a repeater or a hub. So from the PLC, you can connect to a network like this and have a bunch of daisy-chained components, and then you can, from the other port, you can go out to a hub, and you can fan out to a bunch of components. And this is a perfectly valid network in Powerlink, and this would work just fine. So you can have star topologies, or straight line topologies, or ring topologies. Now, when it comes to high availability, there's 3 forms of high availability in Powerlink. The first one is the simplest. It's called ring redundancy. And in this case, if we daisy chain a bunch of components together and take the last component on the network and connect it back to the master, you form a ring. But this is a special kind of ring because now when you put out a pull request, you can listen to it on the other end. If the pull request does not arrive, you make the assumption that one of the cables on the network is broken, and then you start transmitting to both sides. So you can immediately recover from one cable on the network being broken, and the machine can continue to run, but at the same time you know that there's a broken cable, and so you can call for help, but the machine does not go down. In the case of full medium redundancy, you can duplicate the network, so you can have 2 parallel networks, and each component is connected to both networks through a link selector. The link selector can determine when a network goes down and automatically switches to the next one. The third form of redundancy is the redundant master. So you can have up to 9 additional masters on the network. If one master goes down, the next one takes over and that happens seamlessly. So when it comes to electromagnetic noise, with Powerlink, each frame on the network contains data from one item, one networked item on the network. So if you have a spike of noise and you lose a frame, you only use one packet of data. So you're only losing data from one item. Whereas if you compare this to other real-time networks such as Circos or EtherCAT, those are some frame technologies. So there's one frame that goes around the network and collects data from everybody. Now, if you lose that frame, you end up losing data from the entire cycle. So you lose a lot more data when you lose a frame. So if you plot the amount of data that you're losing and compare that to the number of nodes that you have on the network, you'll find that your data susceptibility goes much, much higher and grows much faster. Whereas in Powerlink, it's linear. In these other networks, as you add components to the network, your system becomes very, very noisy, and then you start losing packets, and after a while, your network is simply not functioning anymore. When it comes to commissioning and maintenance, again, because we are using hub technology and because we're using broadcast communication, you can take a tool like Wireshark, which is a free tool, and you can just put it on your laptop and plug your laptop anywhere on the network into any of the hubs. If you do that, you can see all the network traffic taking place in front of you with the right timestamps. So you can see your pull requests, your pull responses, start of cycle frame, all that stuff happening in sequence, and you can immediately tell if there's a component that's misbehaving on the network, whether it's misbehaving by having a lot of jitter or if it's just slowing down or not responding at all. It immediately shows up on your screen. Powerlink in of itself uses, if you think about it from the OSI model, there's a layer 3 gateway that basically sits there and becomes like a gateway between the IP communication and the Powerlink application itself, which is a layer 7 application. And as you can see here, it's actually, we have terms like PDO and SDO because Powerlink is actually CAN open over Ethernet. Now, when it comes to hardware, you need specialized hardware to run Powerlink if you want to have a very high frequency cycle with no jitter. So generally, the interface to the network can happen through any of the FPGAs out there. So generally, things like the Cyclone 4, Cyclone 5, or the Spartan 6, or the Zinc from Xilinx. But then there's also some specific ASICs on the market, like the Citara platform from TI, or the NetX platform from Helsher, or Anybus from HMS. As an example for a use case, there's a company called Bruckner that develops a plastic stretching machine. This is plastic that's used in TV screens, so it has to be very uniform in the way it's stretched. In this case, the machine has 728 axes of motion that are stretching in closed loop. And in this case, you're running at a cycle time of 400 microseconds. So you end up with a very, very fast system. Even though you have a lot of axes, you can still maintain a very high frequency network. One thing that's interesting that happened in China in 2011, the Chinese government made Powerlink a GB/T protocol. GB means that it's government approved, /T means it's government recommended. So this was the first protocol in China to become government recommended, and because it's open source and widely used, it became huge in the OEM industry in China. And so a lot of OEMs today in China are using Powerlink. And we get a significant amount of downloads, something like 24,000 downloads a year from the Powerlink network website just from China alone. The protocol is maintained by the Ethernet Powerlink Standardization Group, which is an open vendor group. And we maintain two standards. One is Open Powerlink, two is Open Safety. It's for safe communication. Both standards are open source. Open Safety is 2 certified, so 3 compliant, performance level E. And so there are, like I said, a lot of OEMs around the world today using Powerlink. We estimate that there's about 3,500 OEMs today with probably more than 2 million systems deployed. If you take a look at the market share today for Powerlink, well, for industrial Ethernet in general, Ethernet IP and Profinet are by far the dominant players, but those are not real-time applications. The real-time applications basically sit here between Powerlink and EtherCAT. So I'm going to pass the control now to Siddharth from Callisto, and he will talk about how you can adopt Powerlink and what's available in the open source domain today.
Thank you, Sari, for the great introduction to real-time Ethernet and how Powerlink fits in well with the requirements of a real-time industrial networking system. Now we will start with the agenda for the quick start with Open Powerlink, where we give some practical ideas on what are the open source Powerlink resources that are available to help engineers develop their Powerlink solutions and bring them to market faster. And then we will also go through some of the guides that are already hosted at Callisto's guides page, and see how that will help engineers develop some of their designs on the various semiconductors available in the market today. So the first question comes is, where do I start when I want to build a Powerlink solution? So if you are a system integrator or an OEM looking for off-the-shelf components to build your machine, you could talk to a company like P&R for their proprietary Powerlink components, which are ready to go as part of the standard systems. Let's say you're a system integrator OEM who's looking to build custom-built components into your system, where for legacy reasons you have a sensor or an actuator in place in your machine, and you want to add Open Powerlink capability to it to talk to other Powerlink components that you might standardize on. In this case, you could use the open source Powerlink resources to add a Powerlink communications capability to your system. And the third case, if you are a sensor or an actuator manufacturer, example encoders, drives, temperature sensors, etc., you could either go with the option of using the open source Powerlink resources and a semiconductor of your choice, or you could choose a module off the shelf from vendors like Hilshire or HMS, etc., to go ahead with your design. Now moving on to what resources are available to build your solution if you're going for the choice of using Open Powerlink resources, there are three items to be considered here. First and foremost is the software stack that you need to implement Powerlink communications into your device. So for the stack source code option, for the managing node and for the control node, which is the master and the slave in the Powerlink communications network, Open Powerlink is the open source software stack source code that is available for both the x86 and embedded platforms such as ARM and FPGAs that are available in the market. Then, based on the requirements of the network, let's say you're having a PLC system and you need to design or configure the nodes in the network such as your actuators or your slaves, then you need a configuration tool to enable the configuration to be loaded onto the PLC. For that, there is an open source configurator tool based on the standard Eclipse platform called Open Configurator. And coming on to the case where you need some hard real-time deterministic performance from your device, you would be advised to go with FPGA-based implementations where acceleration IP cores are available to enable sub-microsecond jitter and response times, and also for the perspective of easier and cost-effective wiring in the field, you need to have daisy chain connections where an integrated hub is available as an FPGA IP core. And finally, when you put all these components together and build your own open source Powerlink device, and you need to take it to market, there comes the question of it being conformance tested or compatible with other Powerlink devices in the market. For this, there is available the open source conformance tool called Open Conformance from the Ethernet Powerlink Standardization Group, which is the standards body behind Powerlink, which can help you test your device for conformance with other Powerlink devices. And the best part of it is all that all of these components are available BSD licensed, which means when you take any one of these components and develop your product with Powerlink, you are not obligated to release the source code of your product back into the market, which becomes a competitive advantage. And to the best of our knowledge, Open Powerlink protocol out there which has both the managing node and the control node stacks available in open source. So having answered the question of what resources are now available to help you build your solutions, we can next move on to some of the guides that are hosted at calisito.com/guides, which can help you with a very quick start to building Open Powerlink on some commercially available off-the-shelf embedded boards and see how you can get quick started with prototypes on your desk. So at calisito.com/guides at the URL, you can go and find access to 4 quick start guides across the platforms. As you can see, the first one is for the Raspberry Pi 2, which is a great platform if you want to have a quick start in building with a very low cost evaluation board that is available off the shelf, and you want to use Linux, which is a very comfortable development environment for many engineers, and you want to build a master and a slave, and you want to toggle a few IOs to check the working of Open Powerlink. And moving on, if you want to move into higher performance designs, you have the option of moving in for the Xilinx Zinc platform or the Ultra Cyclone 5 SoC platform. And going on, we will finally look at the redundancy system, because as mentioned in the previous slides, for power critical applications like a hydroelectric plant or a thermal power plant, or even machines where downtime is very expensive and you cannot afford to have it, you need a master redundancy scheme in place. And Powerlink happens to be the very first open source protocol which also makes the master redundancy source code available for companies to take and develop redundancy as part of their Powerlink products. So getting into the topic on how you can quick start with your Powerlink evaluation on low-cost Raspberry Pi boards. From the guides page, you can navigate to the page which gives you the pre-built binaries for quick start on Raspberry Pi 2. So the objective here is to see how we can enable a very quick start within 15 minutes to have a desktop demo available so you can quickly evaluate Powerlink without going through the build process at the very beginning. So from this guide, you can see that the listing includes the hardware that you require for the demo and the software resources you need to download right from the operating system on the Raspberry Pi to the environment setup for the compilation and finally executing the Powerlink demo. And you also have the detailed set of commands from step 6 onwards to run the Powerlink binaries on the Raspberry Pi and also to take your cycle time measurements. Then once you have had a quick evaluation of a pre-built demo binary on the Raspberry Pi using a couple of boards as managing and control nodes, then let's say you want to move on to building the Powerlink demo right from source, because Open Powerlink stack is available as a BSD licensed source code. Then you could move on to a more detailed quick start guide where all the steps are listed step by step to help you build Powerlink binaries from source for the Raspberry Pi 2. Again, a complete step-by-step process is provided. And then once your evaluation is completed on a low-cost platform such as the Raspberry Pi 2, which helps you get a quick start, you could move into more advanced platforms like the Xilinx Zinc SoC, which helps you get hard real-time deterministic performance for your Powerlink node implementations. Same as before, for the Xilinx Zinc, again, you have 2 reference designs available, as you can see. One is for the Linux master and the other is for the non-OS master. The Linux master is intended for those who are already familiar and comfortable with the Linux operating system based development environment where you might already have a HMI or a GUI application that you need to put on top of your industrial Ethernet device. And the non-OS master is for those reference designs where you want much higher performance levels and lower cycle times and lower jitter responses. So we're moving on to the Linux master. You have a snapshot here showing all the components that you need to get quick started with the environment for setting up a Zinc Linux Powerlink master, where you need the ZC702 development board from Xilinx, which is available off the shelf, and you need a network switch, and you can use 2 Linux PCs as slaves in this case, and another development PC to help you build all the software and load it into the boards. Now, to be noted here is that the network switch is suggested here for the purpose of easily acquiring the hardware required for the demo, but once you've established this setup, it is always recommended to move on to an Ethernet hub for lower latencies. Now moving on, to the resources that are required for building the Zinc Linux master, again, all the steps, all the hardware items, as you can see, are listed on the screen that list every single item you need to build the software and every piece of hardware you need to set up the network for the Zinc Linux Powerlink master. Right from the hardware requirements, the software requirements, and even in this case, the pre-built binary packages are available to help you get started quickly without building the source code on day one. And finally, all the way to running the demo with the master and the slave executables. So once this is done, the next option for the Zinc Linux design, we will move on to the non-OS design for Powerlink. Again, you have options for building from source for the Zinc Linux design, same as before, all the way from the hardware software requirements and going to compiling the Powerlink Linux demo and running it on the system. And moving on, we will have the architecture of a non-OS Zinc Powerlink master or managing node that helps you get a much higher level of performance with lower cycle times. So here you can see a quick snapshot of the architecture of the Zinc Powerlink master on a non-OS platform, where you can see that the process data, service data, and object dictionary and user application modules are all running on the ARM A9 processor in the Zinc subsystem. And the real-time deterministic parts of the Powerlink stack, such as the data link layer and the MAC layer, are all implemented in the programmable logic as accelerated IP microblade software processor. So this shows you the architecture of the Powerlink master in a non-OS bare metal environment on the Zinc device. And once we have seen the capabilities on Zinc, the next option that you want to have vendor neutrality is to also look at a Powerlink master design on the Altera Cyclone 5 SoC, again from callisto.com/guides, which is the easy referral link. And moving on, you have the same non-OS master as you've seen for the Zinc design for the Altera Cyclone 5 SoC. And the architecture for the Altera Cyclone 5 SoC is shown here, are similar to the Zinc design. You have the non-time critical parts of the Powerlink stack with the user layers implemented on the dual ARM A9 section of the Cyclone 5 SoC, and you have the time critical layers of the stack and the DLL below implemented in a softcode NEOS plus accelerated IP system in the programmable logic of the Cyclone 5 SoC to give deterministic performance of the Powerlink stack. This again is a bare metal environment for those interested in a hard real-time system design for the Powerlink master or managing node on the Cyclone 5 SoC from Altera. So again, you see the listing of the hardware and the software requirements and the pre-built binaries and step-by-step instructions are available at the URL for running the non-OS Powerlink master on the Cyclone 5. And then coming to the last option that is available on the guide is the open source master redundancy design. As we mentioned, this is the first ever open source code based implementation available for implementing a redundant master design on your PLCs. So shown here is an illustration which shows a standby master and an active master in the normal operation of a PLC, where PLC 1 becomes the active master. In the event of a failure of the active master PLC 1, the standby master PLC 2 can take over and become the active master to ensure seamless operation of the machine and avoid downtimes. And also to be noted here is that the Open Configurator configuration tool, which is available as an open source utility with Powerlink, is also having inbuilt support for generating the configuration that is required to support redundancy. Again, in open source and a segment first. And all the resources that you need in terms of the hardware and software and binaries to download, compile, and build, as well the demo for redundancy for the Raspberry Pi 2 hardware as an easy, accessible piece of device is available for you at the guides at callisto.com for the redundancy demo. Now, having seen the 4 demos that you have, you can also find access to the link for these 4 demos: the Quick Start on Raspberry Pi 2, the Xilinx on Zinc, the Altera Cyclone 5 SoC master, and the open source redundant master for Powerlink. The links for these 4 tutorials are also available through the Ethernet Powerlink Standardization Group website at www.ethernet-powerlink.org/en/powerlink/tutorials. It's another link for you to get access to the same tutorials at the Callisto Guides page. And to give a quick brief on Callisto's association with Powerlink, Bhagat, our CEO, has been a part of Powerlink since 2005. He had experience in specifying and implementing the world's first open high availability solution, master redundancy. As Callisto, we are associated with Open Powerlink stack development and also support with the online SourceForge forums since 2008. Coming to Open Configurator, the first open source version of the network configuration tool was released on a TCL/TK development in 2009, and in 2014 we have followed up with a more powerful 2.x version to help customers use Open Configurator on standard Eclipse IDE. And since we have spoken quite a bit about how to use open source Open Powerlink resources using off-the-shelf commercially available development boards to build your industry Ethernet devices, here's one screenshot which shows you how we demonstrated the possibility of using such open resources to build a distributed motion control demo using off-the-shelf embedded hardware from Analog Devices, the Altera. This was demonstrated at the Ethernet Powerlink stall at Embedded World 2015. And to help you with a quick start, once you manage to use the guides that are hosted at callisto.com, we hope you'll be able to get some quick prototypes up and running on your desk. And if you'd like some consulting or knowledge transfer to help you take yourself ahead with your development to taking your product to market using Open Powerlink, we are happy to help customers across semiconductor, actuators, drives, PLCs, and also system integrators and machine builders realize their designs with a faster time to market. And that brings us to the end of the session here, where we are also like to announce that we are in the US in October 2016, and we would look forward to meet the participants and those interested to help them with the industry Ethernet and IoT implementations to see how they can build on top of our quick start guides free of charge and how they can use that to move forward with their developments. And that brings us to the end of this part of the webinar, and I would like to leave it open to questions and handing over to Joanna. Thank you.
Thank you, Siddharth, and thank you, Sari. Yes, at this time we would like to open it up to questions for the audience. If you have a question for either Sari or Siddharth, please type it in your questions panel, and we will leave a few minutes for some Q&A here at the end. I have been noting a few questions that have come in already, so I'll start with those while we get a few more in. My first question that was given goes over to you, Sari, which is, what is the advantage of an open source protocol?
So there's a few Ethernet protocols today on the market, and they are all proprietary. So Powerlink is really the only one that's open source that is feasible in a machine. And not only is it open source, but it's open source and it is very widely used in the marketplace. So if you need off-the-shelf components, you can get drives from many people, IOs from many people, PLCs from many people running Powerlink already. So if you're not designing your own system from scratch and are looking for off-the-shelf components, you can also do that. So this level of openness and the fact that there are no royalties associated with this makes Powerlink quite a formidable protocol, especially when you consider the performance that you get out of it.
Great, thank you. The next question that came in asks, why is node-to-node communication important?
So if you're trying to synchronize, say, several axes of motion running at the same time, let's say you have several shafts in a mechanical system, people sometimes would use a set of gearboxes that connect the shafts together. In Powerlink, you don't need to do that because of this high-speed synchronization where each node can see what the other node is doing. You can just synchronize everything electronically, so it makes it a very cost-effective way to synchronize components.
Thank you for that. Siddharth, this question is for you, and audience has asked, can the Raspberry Pi be used as a deterministic power link node?
Yeah. The Raspberry Pi is not intended to be used as a deterministic Powerlink node because of the way the architecture is built, and it uses a USB to Ethernet converter in its architecture. But the purpose behind recommending the Raspberry Pi for a quick start is that it's a very low-cost piece of hardware which enables development on Linux, and hence, to learn about the functionality of Powerlink, it's a very good way to quick start. Hence, we would suggest you move with FPGA-based platforms or other ARM processors to get more deterministic performance implementations.
Great, thank you. Next question is also for you, Siddharth. What is the difference between single and dual processor Powerlink node designs?
Coming to an example of a use case to better explain this answer is assuming a use case where you have very simple I/O blocks in place. A single processor-based implementation is very well able to handle the processing load of the Powerlink stack as well as the user I/O application. But when you move on to more complex applications like motion control or vision system as a control node, then it's advisable to have two separate processors, with one processor handling the Powerlink stack and network processing communications, and the other application processor handling the user application for the image processing or for the DSP for the motion drive. So in those cases, you would prefer to go for a dual processor application to ensure that neither the user application nor the network performance is compromised.
Great, thank you. And I think we have time for one last question for this live portion. Comes in from the audience and asks, how scalable is Powerlink and what is the max number of devices or nodes?
Okay, so in the largest possible network, you can have one managing node and up to 239 control nodes in a Powerlink network. From a practical perspective, you generally don't do that. You generally might have several networks that are synchronized together, but if you wanted to have a really large network, you could do that.
Great, thank you, Sari. Well, at this time, again, if you had any further questions, please feel free to email us those. And I would like to thank Sari and Siddharth as well as our webinar participants, and of course our exclusive sponsor, B&R Industrial Automation. And as a reminder to everyone on this webinar, it has been recorded and a link will be sent to you with that recording within the next 24 hours. If you did have any questions, please feel free to email those out to us. And don't forget the MCMA Technical Conference is coming up in New Orleans, October 11th through the 13th. This conference offers solutions to your engineering problems. Attend and learn about new technologies and best practices and see the latest products. Spaces are limited, so be sure to book your seat today. And lastly, visit www.motioncontrolonline.org for more information about our conference or upcoming webinars. Thank you again and have a great rest of your day.